Hello everyone, we are Group 2 and our topic is image enhancement and restoration. And firstly, the process of image enhancement. The process of image enhancement involves a series of steps to improve the visual quality and clarity of a digital image. First, image acquisition. The image is captured using a camera, scanner, or other digital device. Second, preprocessing. These techniques are applied to a raw image data to address issues like low contrast, noise, and color imbalance. Third, feature extraction. These algorithms then identify key elements within the image such as edges and textures. Fourth, Fourthly, these features are then enhanced using specialized algorithm that sharpens, smooth, or otherwise modify the image to improve its visual quality. Finally, post-processing steps are taken to ensure the enhanced image meets the desired quality standard before it is displayed. And this figure shows the process of image enhancement. Now moving on to the process of image restoration. It involves three steps. Step 1, image acquisition. The first step in the image restoration process is to acquire the degraded or corrupted image. This can be done through various means such as digital camera, scanner, and the goal is to capture the image in a digital format that can be processed and analyzed. Step 2, degradation model estimation. Once the image is acquired, the next step is to estimate the degradation model that has affected the image. This involves analyzing the image to identify the type and extent of the degradation, such as blurring, noise, or geometric distortion. The degradation model helps to quantify the specific impairment that need to be corrected during the restoration process. Step 3, restoration algorithm application. With the degradation model in hand, the appropriate restoration algorithm can be applied to image. These algorithms are designed to reverse the effect of the degradation using techniques such as deblurring, noise reduction, or geometric correction. The goal is to recover the original high quality image as accurately as possible.
Now I'm going to talk about block diagram of image enhancement system. A block diagram for image enhancement typically showcases the different stages involved in processing an image to improve its visual quality. Here is the block diagram where first it is input image. This block represents the original image that needs enhancement. Then it goes to pre-processing, which is optional. In some cases, pre-processing steps might be present before the main enhancement techniques. This could involve noise reduction to remove unwanted artifacts or color space conversion to prepare the image for specific enhancement algorithms. Then it goes to Fourier transform, where we take the original image and convert it into its building blocks using Fourier transform. These building blocks are like sine and cosine waves, each with a specific frequency. Then it goes to filter function. Imagine a toolbox with different filters, each allowing certain frequency to pass through and blocking others. We choose a filter based on what we want to enhance. A blur filter blocks high frequencies while letting low frequencies pass, smoothing the image. Conversely, a sharpening filter allows high frequency to pass through, enhancing edges. After applying the filter, we use the inverse Fourier transform to recombine the modified frequency back into an image. The result is an enhanced image based on the chosen filter. Then, post-processing, which is also optional. Similar to pre-processing, some methods might involve post-processing steps after the main enhancement. This could involve sharpening the enhanced image. Lastly, it is output image. This block represents the final enhanced image after processing through the different stages. The specific techniques used within the enhancement block will depend on the desired output For instance, if the goal is to improve the visibility of details in a low light image, contrast enhancement techniques would be prominent. Next, it is block diagram of image restoration. An image restoration block diagram typically focuses on recovering a degraded image back to its original state. Firstly, it is input, which is an input image. This block represents the degraded image that needs restoration. Second, it is degradation function. In some cases, this block might represent the process that degraded the original image. This could involve functions describing blur, noise, characteristics, or other distortions. Understanding the degradation helps choose appropriate restoration techniques. Third, it is restoration filter. Restoration filter acts as a toolbox. Different filters target specific problems. Some, like inverse filtering, try to undo the blur but make the noise worse. Others, like winner filtering, find a middle ground between removing noise and keeping image details. And deconvolution filters specifically address blur caused by camera movement, while wavelet based restoration for effectively removing noise while keeping sharp edges. Lastly, it is output image. This block represents the final restored image, hopefully closer to the original image before degradation.
Now let's talk about result on the image enhancement. Number one is pre-processing. In the contrast adjustment, this will improve the visibility and distinction of image details by increasing the difference between light and dark areas. Next is noise reduction. This results in a smoother image with fewer random variation. This makes key features more clear by eliminating graininess and other unwanted artifacts. This is vital for applications requiring high precision such as photonic analysis and scientific research. The last is color correction. This balanced color produces a more natural and visually appealing image. Correcting color imbalances helps in accurately representing the true colors of the scene, which is important for tasks like artistic creation. Number two we have is feature extraction. In the edge detection, which provides a sharper definition of object boundaries, facilitating better recognition and analysis. This is crucial in areas like object detection in autonomous vehicles. Next is texture identification. Enhanced patterns and surface details are particularly useful in various analytical applications such as material science and geology. The last is region of interest identification, focusing enhancement on critical areas of the image such as specific object or features, allowing more detailed analysis of important regions without unnecessary processing of the entire image. Third enhancement is for the enhancement technique. In sharpening results in crisper image with better defined edges and details. It enhances the clarity of the finished details, making it easier to distinguish between different elements within the image. In smoothing, which reduces noise and minor artifacts, leading to a cleaner image, this process helps in creating a more pleasing image while preserving important details. In terms of histogram equalization, enhanced overall contrast and brightness make hidden details more visible. The fourth result is in post-processing, where the final adjustment will take place, which ensures that the enhanced image meets specific visual standards and requirements. This step includes fine-tuning the image to achieve the desired quality, ensuring that it is suitable for its intended application, whether for publication, display, or further analysis. This is the image of brain MRI, which is before and after. Now let's move on to the image restoration. In image acquisition, digital capture will be accurate, which has a high resolution digital format ready for processing that ensures that image retains as much detail as possible from the original scene. For legacy analog sources, digitalizing old images preserves essential details for restoration, allowing historical or archival materials to be brought into the digital age for further process and analysis. Degradation model estimation, analysis of degradation, identifying blur, noise, or geometric distortion is crucial for targeted restoration. Let's see challenges and limitations. Well, first one, low light condition. Enhancing images taken in poor lighting is tough because details are often lost in the shadows. Next is intricate textures. It's hard to keep fine details and natural textures intact during enhancement without losing their quality. The noise amplification. Aggressive enhancement methods can unintentionally increase the visibility of unwanted noise and imperfection.
Future research directions. To look at the future of image restoration and enhancement using DSP, we will explore three key areas: leveraging deep learning, integrating multimodal data, and the potential of edge computing for real time enhancement. First, let's talk about deep learning. Deep neural networks, especially convolutional neural networks, are transforming image enhancement. By learning from vast amounts of data, these networks can robustly improve image quality. Future advancement could develop more sophisticated models that can handle a wider range of distortions, making enhancement more effective. Next, multimodal fusion is an exciting frontier. By combining data from various sources like infrared and depth sensors, we can achieve superior restoration quality. This approach leverages different data types to create a comprehensive scene representation, particularly benefiting night vision and medical imaging. Finally, let's discuss edge computing. Developing efficient algorithms for mobile devices enables real-time image enhancement. Future research could focus on lightweight, powerful models for edge devices, allowing instant, high-quality enhancement.